When you're dealing with one-sided limits, the limit laws behave more or less in the same way as with the regular two-sided limits. So for limit laws and one-sided limits, if you look at the sum rule as an example, or the sum law, right, the limit as x approaches a from the left of f of x plus g of x is the same as the limit as x approaches a from the left of f of x plus the limit as x approaches a from the left of g of x. And the same thing holds when x approaches a from the right. I'm not going to read each of those because I don't want to bore you, but the idea is that everything that worked for limits, regular limits, without specifying whether we were approaching from left or right, those are called two-sided limits. Everything that worked for two-sided limits works for regular one-sided limits as well. Okay, as long as the limit from the left and the limit from the left of f and g exist, then you can apply the sum rule or the difference rule or the constant multiple rule, the product rule, the quotient rule, and the power rule. Again, with the one care to take when the denominator of a quotient equals to 0 or approaches 0. You're not supposed to have that. The power rule works precisely the same way, but the root rule can sometimes be incorrect or be improperly applied. The one thing to be careful with is that when the root is even, meaning like a square root or fourth root or sixth root or an eighth root, for example, you need to have f positive or at least non-negative in the region that you need, okay? So when x is approaching a from the left, then x is less than a. So you need that to happen for x less than a near a, right? And when x is approaching, so that was supposed to be, there's a typo there, that's supposed to be from the right, and x is bigger than a, right? So that's supposed to say from the right. So what I'm trying to say is when x is close to a, but bigger than a, then you have to make sure that f of x is non-negative for x bigger than a and near a. So it doesn't have to happen for all x. So x needs to be greater than a, near a, which is the x values, or the x values that we evaluate when we're looking at limits from the right or limits from the left. So just make sure that we check for that. It's pretty much the same as one-sided limits, but with this one minor change, right? So I'll give you an example of what we cannot do. Let's say you have, in this root rule, you have some function f that, I don't know, looks like, do the graph in blue, looks like this. Let's say that's y equals f of x. Let's say this is 1, okay? Then you are allowed to calculate the limit of f of x as x approaches, or the root of f of x, right? That's what we're talking about, the root rule. As x approaches 1 from the left, because to the left of 1, the graph is greater than 0 and the root of a positive value is well defined. So this is fine, and if we use the root rule, that's the root of the limit x approaches 1 from the left of f of x, and from that graph the limit of f of x is 0, the square root of 0 is 0. So cool, the root rule does apply. However, if you try and calculate the limit as x approaches 1 from the right of the root of f of x, right? And I'll go with my highlighter now. To the left, or to the right of 1, right? Because 1 plus means x is bigger than 1. We're looking at this part of the graph. These values are negative. So that means you're getting, even though they're very close to 0, they are negative. You're not supposed to plug in negative values into a square root, right? So this thing does not exist, and the root law does not apply. Just this one minor distinction that you have to be mindful of. Okay? Cool. Let's go to an example. Here is this function. We have f of x equals to minus 2x plus 4 when x is less than or equal to 1, and f of x equals to root x minus 1 when x is greater than 1. Let us find both limits when the limit as x approaches 1 from the left of f of x, that equals to the limit as x approaches 1 from the left. X approaching from the left means x is to the left of 1 like this, right? So less than 1. So this is the graph we're using. That's the line graph. That's this one. So that's the limit of minus 2x plus 4. And that one is a linear function. So we know linear functions are well behaved in terms of limits. They are continuous. We're going to expand on that wording in a different video, but we know we can calculate this by direct substitution by doing minus 2 times 1 plus 4. So that's minus 2 plus 4. That equals 2. So this little minus as an upper script on 1 doesn't translate back when you plug it in, right? That's just a symbol for the limit calculation. So if you try and do, let me make maybe it green, the limit from the right now of f of x, that's the limit as x approaches 1 from the right. So when we're approaching 1 from the right, then we're looking at the right side of 1. So x is greater than 1. When x is greater than 1, then we're using the other rule. So we have the root of x minus 1. And okay, x is greater than 1. So that means x minus 1 is positive. So we are allowed to use the root law. And I'll note that here. By the root law, we can use it because x is greater than 1, and that's because we're calculating the limit as x approaches 1 from the right. Implies x minus 1 greater than 0. And that's all we need to check. We need to check that the thing inside the even root is non-negative, right? We didn't even need strictly positive. We could have greater than or equal to, but strictly greater than 0 is better than greater than or equal to 0. So using the root law, we can just do the root of 1 minus 1, so direct substitution now, because now this is a regular linear function. This is the root of 0, so this is 0. So I hope this helped.